Welcome to Topology class. Today we will discuss product topology and projection functions. So first of all, product topology. Already we have discussed, just I will brush it out. So product topology. Suppose you have got two topological spaces. Suppose x2 and yu be two topological spaces. Then the product topology on x cross y is defined as I will denote this with tau dash. Tau dash contains V cross U form set where V belongs to tau and U belongs to U. So this is the one. That is, we are taking open sets from each topology and having the product. Then you will get your collection of such sets. That set is called the product topology. Now we are having here a theorem, 3.6 theorem, projection map. I forgot to say projection map. So that is what's a projection map? Next one is projection map. Projection map means we are having some x1, x2, etc. xn are topological spaces. Now we will denote it by pi I from x to xi is a projection map, is the ith projection map. Ith projection map. So first projection map should be, so pi 1 is defined from x to x1, pi 2 from x to x2, like that. Okay, so pi I from x to xi. That means you are projecting to one coordinate. This is called the projection map. Now here we have got a theorem, 3.6 theorem. 3.6 theorem. Let xi tau I equal to 1, 2, extra up to n be a collection of topological spaces and x tau their topological products. Their topological product. Then each projection pi I is continuous. Moreover, if Z is any space, is any space, then the function, then the function f from Z to X is continuous, is continuous if and only if pi I composition f from Z to Xi is continuous, is continuous for all I equal to 1, 2, 3, etc. up to n. So this is the theorem. So what this theorem says, let X to I be a collection of topological spaces and X to their topological product. Then each projection pi I is continuous. Moreover, if Z is any space, then the function f from Z to X is continuous if and only if pi I composition f is continuous. So first, let us examine the first part of the theorem. The first part of the theorem says that we are having x1, x2, etc. some xn topological spaces with the topology tau1, tau2, etc. tau n. Right. Now we go for the product. So its product means x1 cross, x2 cross, etc. cross xn. Now this set we are mentioning as x, and the topology, corresponding product topology should be there. No, that topology we are naming it as tau, right? So x tau is the product topology. Then we can define pi I from x to xi, right? Now this projection is continuous. That is exactly when you are saying this is tau I continuous. So we want to prove this. So what is the method of proving something is continuous? We should go for x to xi, right? So this is x, this is xi, and x, and my projection is pi I. Now in order to prove this, what we are going to do is we should take an open set here, right? And go for its inverse image, that is pi I inverse. So you get pi I inverse from here means, now if we can able to prove that here also it results a open set. This is open, then its inverse image is also open, means we will say that the function is continuous, right? So let's see how we can prove it. So this is the first part of the theorem. So proof, we have to prove that pi I is continuous. Now let Vi belongs to tau I. That means here the topology. See xi. In xi my topology is tau I. Now you take a open set here, I have said. So whenever you are taking an open set means that should be definitely a member in the topology. So this open set belongs to tau I. So I am taking an open set Vi in tau I. We have to show that pi I inverse of vi is open, right? Is open, which implies pi I inverse of pi vi belongs to, there the topology is tau, right? So the inverse image in X topology is tau. So I should find the inverse image of open set belongs to the topology. Now what about pi I inverse of Vi? But pi I inverse of Vi, right? It should be x1 cross x2 cross extra cross Vi cross xi plus 1 cross extra cross x and y. Why I am taking like this? Because when I am taking this means it will depend only on the ith coordinate. Remaining all I can fix it as x1, x2, etc. Now what about this? Will it be open? Definitely, right? Why? Because I am taking this in x1 cross x2 cross extra cross xn. Vi already open in xi. Now x1 is open in x1, x2 open in x2, right? The entire set belongs to the topology, right? So in each one, x1, x2, etc., xn is open. Now I am having here vi another open set. So when I am having the product of this means, according to the product topology definition, it is going to be an open set, which is open, which is open in X by definition of product topology. Product topology, which implies my pi I is a continuous function, right? Pi I is continuous. So first part of the theorem we have proved. What about the second part? Second part says that, see, moreover, if Z is any space, then the function f from Z to X is continuous if and only if pi I composition f from X to Xi is continuous, right? It's very easy to prove one part, if and only if condition, right? So suppose your f is continuous one, then pi I already we have proved continuity. Now pi I composition f, composition of two continuous function, that will result another continuous function. Therefore, one part is very easy. So whenever you are assuming f is continuous, pi I composition f should be a continuous function since it is going to be the composition of two continuous functions. Now what about the remaining? That is the converse part. That means I want to prove that pi I composition, whenever pi I composition f is continuous, f is going to be continuous. Let us see how we can prove. So here, for the second part, for the second part of the theorem, suppose f from z to x is continuous, is continuous. Then for each I, then for each I pi I composition F is continuous. Since composition of continuous functions are continuous. Since composition of continuous functions are continuous. Now we want to prove the converse part. Conversely, suppose that each pi I composition F from Z to Xi is continuous. Is continuous. Denote pi I composition F as Fi, right? So this we are denoting pi I composition F as Fi. Now to prove F is continuous, right? Now to prove F is continuous. For this, it is sufficient to prove that the inverse image of any member of a base for X tau is an open subset of Z. Can you follow? No. See, we want to prove that F is continuous. So we have got a topology here. Inside the topology, we have got two sets. One set is Z, another set is X. So we are having the function F from Z to X. So in order to prove F is continuous, what we are going to do? Our usual procedure. Usual procedure is we will take some open set here, right? This open set here, and what we are going to do? We will find its inverse image here. That is F inverse of this open set. Suppose it is V. F inverse of V. Now, if this is open here, we will say that this F is continuous, right? So we have to prove F is continuous. So it suffices to prove that the inverse image of any member of a base for X tau is an open subset is an open subset of Z. See, I have said this is X and this is Z, right? Z and this is X. Now we should take an open set here. So here in particular we are taking a base element. That's also open, right? If this is a base element, I'm taking if I am finding that its inverse image is also open, then any open set can be written as union of base elements, right? So union of base elements means its inverse image, all are going to be open. So any open set over here also I can express as union of open sets in set, right? Okay, let me repeat. Here what you're going to do is, as I explained, we should take an open set and go for its inverse image. But in particular, we can have this open set can be written as union of its base elements, right? So these are going to be the base elements. So I take one such base element. Now, if I am proving the inverse image of this base element, suppose here is coming, this base element, inverse image of this base element is open in set. Then I have proved open inverse image of open set is open. Why? Here, suppose I am having here V1, V2, V3 and V4. So basis elements, I am writing my V as union I equal to some 1 to 4 of Vi. Now this Vi belongs to base element. Now suppose I am having F inverse of Vi, that's equal to some Ui open. Okay, Ui is open. Now I should write some F inverse of V, and we have studied that inverse image commutes with union and intersection. So this is union I belongs to 1 to 4 F inverse of Vi. Now Vi I have find it out as Ui. So this is equal to I equal to 1 to 4 Ui. Now each Ui is open. Now what about this union? Is open. So my F inverse of V is open. So this is the procedure. So it is sufficient to prove that the inverse image of any member of a base for X tau is an open subset of Z. Now, now a base for product topology, because we have to take the open set base in the product topology set. Sorry, product topology X. Base for the product topology consist of all sets V of the form V1 cross V2 cross etc cross Vn, where each Vi belongs to tau I for I equal to 1 to etc up to n. Now, for Z belongs to Z, f of Z belongs to V. If and only if pi I of f of Z belongs to Vi. Am I true? F of Z belongs to V, then the projection of f of Z should belongs to Vi, right? Then only my f of Z belongs to V. For all I equal to, for all I equal to 1, 2, 3, etc. up to n. In other words, f inverse of V can be written as intersection I equal to 1 to n fi inverse of vi. Fi means pi a composition f we have denoted as fi. So this can be written as fi inverse of vi. But each fi inverse of vi is open by assumption, right? Since fi is assumed to be continuous. Assumed to be continuous. Hence, what you are having? Hence, f inverse of v being the intersection of finitely many open sets is open in Z, should be open in Z, which implies f is continuous, hence the proof. So we have proved that the projection function in a product topology is continuous. Next we are having some definition. 3.7 definition. Let x, y be spaces. Spaces means topological spaces. A function f from x to y is said to be open. Can you guess? Or relatively closed. If whenever A is an open or respectively closed. A closed subset of X comma f of A is open or respectively closed. Subset of Y. So it says that when we will say that a map or a function is an open map or a closed map. So we have got two topological spaces here, X and Y. So here I have got a topological space. It's my X, and the one I have got it as Y. Now X to Y I have got a function f. So when I will say this function f is open, that's our question. So for that, what you have to consider is, I should consider here an open set A, right? Now go for its image here. So I will get something here as, suppose this is my f of a. Okay, so for a, I have mapped this to f of a. Now for every a open in X, f of a open in Y. This implies f is open. Okay, now reversely means for every a closed in X, if I am having f of a is closed in Y, then we will say that this map is a f is closed. This map is a closed map. Here, open map means image of every open set should be open. Okay, hope you understood this. So only we are taking care of the definition here. Next definition is next one proposition is the 3.9 proposition. 3.9 proposition. Let x, comma y be topological spaces and f from x to y a function, then the following statements are equivalent. In the following statements are equivalent. First one, f is a homeomorphism. F is a homeomorphism. Second one, f is a continuous bijection. F is a continuous bijection. And f is open. Third one, f is a bijection. F is a bijection and F inverse is an open map. And fourth one, there exists a function. G from y to x such that f comma g are continuous and G composition f that's equal to identity function in X and f composition G is equal to identity function in Y. So what was the homeomorphism? Homeomorphism means we have already discussed this homeomorphism. Homeomorphism. Suppose you have got two topological spaces x and y and f from x to y. Now if f and f inverse are continuous, we say F is a homeomorphism. Homeomorphism. Now with this definition, just to check what are the given equivalence conditions. Okay, so first condition, F is a homeomorphism. Second one, F is a continuous bijection. That means F is continuous, right? Since F is a bijection, we can define its inverse image also, right? Now for inverse image, it's given that F is open. So since F is open, means it will map the open sets to open sets only. So when you're taking the inverse image of open set, you will get again an open set. So F inverse should be continuous. Now the third one, F is a bijection and F inverse an open map. The same way. Now fourth one, there exists a function g from y to x such that F and g are continuous. Then these two follows very easily, right? F and F composition, sorry, F and F inverse. That is, G is nothing but F inverse. Okay. Next, we have got one more definition. What definition is 3.10 definition. So the previous one directly follows from definition, right? Proof, we can write follows from definition of homeomorphism. Okay, now pass to next definition. Let X tau and YU be topological spaces, topological spaces, and embedding. Spelling is embedding, or another name is embedding, imbedding. Both are the same. Either we will say that embedding or embedding of x into y. X into y is a function e from x to y, which is a homeomorphism, homeomorphism when regarded as a function from x to onto this range space, that is onto e of x comma u restricted to e of x. Okay, so this is called the embedding or embedding. So definition says that you have got x and y, two topological spaces, and a map e from x to y. So when you are restricting this e to the range of x, if you are getting a homeomorphism, we will say that this e is an embedding. I repeat, we have got two topological spaces. One is x and another one is y. So x and y. Now from here to here, you are having a map e. Now whenever you are having the topological space and e, you can go for the range of x. So suppose this is going to be the range of x, that is e of x. Now when you're considering E from x to E of x, if this E will result a homeomorphism. Homeomorphism. Then E is an embedding. Can you follow now? So you will say that E is an embedding whenever this E is restricted to the range. E is resulting a homeomorphism, means we will say that this is an embedding. So we are having one more proposition, 3.11 proposition. Proposition. A function E from x to y is an embedding if and only if it is continuous and 1 1, and for every open set V in X, there exists an open subset W of Y such that E of V is equal to W intersection E of X. W intersection E of X. So what this proposition says? A function E from X to Y is an embedding if and only if it is continuous. First one, right? So embedding means by definition E restricted to E of X should be a homeomorphism. Homeomorphism means definitely it should be continuous and 1 1. And for, since it is 1 1 and we are taking only the range, it should be onto. So you can define your inverse image. And for every open set V in X, there exists an open subset W of Y. Okay, such that W intersection E of X is E of Y. So it is nothing but follows from the definition of homeomorphism and relative topology, because we are taking the open set as W intersection E of X. So proof follows directly from definition of homeomorphism and relative topology. So today we have discussed uh, first of all the concept that the projection function in a product topology is continuous. Secondly, we have taken few more definitions, that is what do you mean by an open map and a closed map and a homeomorphism. Next, a proposition. So homeomorphism 3.8 definition. Okay, so homeomorphism definition. Okay, I missed the homeomorphism definition here, right? So you can note it down. Homeomorphism definition is the, let me write it here. Definition is actually 3.8. It is homeomorphism. Since I haven't mentioned it here because we have already discussed it in your starting stage. A homeomorphism, a homeomorphism from a space from X to Y is a bijection, F from X to Y such that both F and F inverse are continuous, and X is said to be, and X is said to be homeomorphic to, homeomorphic to Y. Okay, so this is the definition of homeomorphism, and we have seen the propositions, equivalence condition of homeomorphism, and next to definition of embedding, and a proposition regarding embedding. Okay, so with this I'm winding up today's session here. Thank you for your patient listening. Thank you.